This is the rope passing through a capstan on a dock attached to the boat. The rope is pulled in and at a constant rate. This is the rate of the rope. And the capstan is 6 feet vertically above the water. How fast the boat traveling when it is 9 feet from the dock? Right? How do we put them together? This is the boat, the dock. Okay. And the capstan attached to a boat offshore. Okay, the rope is pulled in at a rate 4 feet 4 feet per second, and the capstan is 6 feet vertically above the water. So here 6 feet. Okay, 6 feet. The rope and water. Good enough. Okay. For this diagram, the rope is pull up to the top of the capstan. Okay, 6 feet above the water. So we know the length here is 6 feet. And then as for how fast the boat traveling, that means when you pull, that means the boat is traveling closer to the deck, to the dock. Okay, coming this direction while it's pulling up the rope up to the top of the capstan. Okay, so this is about the right triangle diagram. Okay, the vertical side here is 6 and asking for the rate of change of the boat coming toward to the dock where the length or the distance away from the dock 9 feet. Okay, 9 feet. Okay, this is the boat. This is the dock. Okay, what do you know here? The rate of the rope that is pulled in is 4 feet per second. So right here, 4 feet per second. Okay, and think about the real situation. When you pull, that means the distance getting shorter and shorter, right? Gonna be the distance can be negative inside. That means the position of the boat is closer and closer and closer to the dock. Make a list as before. Now we're gonna introduce a notation. We're gonna find the rate that the boat traveling when it is 9 feet from the dock. So we're gonna need to know that the notation for the distance between the boat and the dock. So let it be x. Let it be x. Okay. And we're gonna find so the known number or the given number, the given information, the rate of change over here. If we have this as a x, I'm gonna write this as a y and this is as a z. Okay, like the diagram like x, y, and z. So the rate of change of the z or the dz dt here equals 4, but negative inside. Why negative inside? Because again, the position of the boat getting closer and closer to the dock. So that means the distance here is shorter and shorter as well. Okay, unit is feet per second. And then what we don't know, we're gonna find out. This is unknown. Unknown gonna be how fast, which is the rate of change of the x or the rate of change of the boat, the distance that the boat away from the dock, or the dxdt. We are looking for it when x equals 9. When x equals 9. Now, what variable that we have in this situation? We have x, y, and z, right? We have x, y, and z. X is changing, is moving. 9 is at the last position that we are looking for the rate of change. So basically, X is not 9 to begin with. It's going to be the variable X. I'm going to leave it as a X here. So we have X, we have 6, we have, because the height of the capstan, no change, it still remain as a 6 as the boat moving closer and closer toward to the dock. Okay, so if we look at the diagram, X here, 6 here, and then Z here. What the relationship of X and Z and 6? What do you think? What would be the equation that get them all together? Anyone? Mm, sorry. Can you think of any equation that get X, 6, and 7 all together from the right triangle diagram? No response. So think about the right triangle. What equation? Oh, there you go. I saw Jeff. X squared plus y squared equals, yeah, is squared. Pythagorean theorem. Thank you. So right now from the notation I put in a diagram, we're gonna use it as x squared plus the 6 squared equals z squared. Okay, that's very good. Thank you, you guys. So the unknown will be x and the z. Well, from here, let's see what we need to know. Um, right now we have the equation as a Pythagorean theorem. So next, for the implicit differentiation, we're gonna find the derivative of each term with respect to t. All right, the d by dt of x squared plus d by dt of 6 squared plus d by dt of z squared. The derivative of x squared is 2x times dx dt. Derivative of 6 squared, the constant derivative is 0, or this is equal sign, equals the right hand side to z dz dt. This we're gonna need to know what z in the content when x equals 9. So I'm gonna add another slide here. Diagram again. So this is 6, this is x, this is z, as x squared plus 6 squared equals z squared. And from the implicit differentiation, we have 2x dx dt plus 0 equals 2z dz dt. So at x equals 9, we have the diagram at 9 here, 6 here. We're going to find out what the z. The z by the Pythagorean theorem, z is 6 squared plus 9 squared. Right? Pythagorean, because z is the hypotenuse. So we got 36 plus 81, or square root of 117 in the square root as a z value. So now another known number that we know, x equals 9, z equals square root 117, and dz dt provided as negative negative 4 feet per second. Negative 4 feet per second. Negative sign because it's moving toward to, like, coming closer and closer to the dock. So the distance is decreasing. So in the decreasing way, so we put negative sign. So this derivative simplified to be 2x dx dt equals 2z dz dt. And we are looking for dx dt. Rearrange it, divide all by 2x. We have dx dt equals 2z divided by 2x, where 2 and 2 can be gone, can be reduced. And now we find dx dt by replacing z with the square root of 117. Replace x with a 9. Replace dz dt by negative 4. Plug in the numbers, calculate the numbers. It should be, let's see what number that we get. It should be negative inside because the position of the boat is getting closer and closer to the capstan or to the dock. Uh-oh, sorry. Whoops. Sorry. So negative 4 multiplied by the square root of 117 and divided by 9, we should get negative 4.8. 1 as two decimal places. And the unit of the x per unit of the time, from the problem, unit of the x or the distance is in feet and the time is in second. So it's going to be feet per second. The sign negative means the rate is decreasing. So decreasing, okay, or coming toward to the dock.